Rabia Ocean, Faikar Jeffar, Tarek Barcode. So Rabia, you have a 15 minutes for presentation and 5 minutes for a question. So please start.
Okay, thank you very much. Hello, everyone. I am thrilled to share with you my presentation entitled Modeling Accurate Prediction of Junctionless Infrared Phototransistor Performance Using Explainable Deep Learning Regression Models. So the presentation outline will be like that. I will start by an introduction and background. After that, we will describe device structure and modeling methodology procedure. Then we will talk about deep learning modeling and analysis of phototransistor properties, and then we conclude by a conclusion. So the main challenge in optical wireless communication systems is optical receivers' substantial power dissipation. This challenge necessitating power losses in electric, but it is producing by power losses in wire electric wires and of course producing signal attenuation and information distortion of inter-chip data communication. This challenge necessitating implementation of signal processing techniques to optimize the transmission information. To address that, we will use a FET-based phototransistor are considered the most promising among several optical structures. So the planar junctionless structure in that kind of FET phototransistor sensor-based application, facilitating robust clearization, presenting cost-effective and providing larger and more accessible surface area. All those will be given by efficient photo detection and simple fabrication process. And also the critical challenge, another critical challenge is there. It is related to a planar junctionless phototransistor, is the uniform high channel doping due to the influence of fluctuation in design parameters of optoelectronic device performance. To enhance planar junctionless phototransistors, innovative design methodology development are needed. Then this innovative methodology will reduce the fabrication cost and optical and electrical and improve optical and electrical performance. The development of a deep learning guided optimization strategy is done to improve the optoelectronic performance of planar junctionless phototransistor. It is opted to combine accurate two-dimensional analytical and numerical simulation with the advanced DL operation. Those two lead to investigate key design parameters impact on device performance. So the IR sensing device showed here in this figure one, it's a cross-sectional view of the analyzed junctionless phototransistor dimensional view. Is considered with a germanium gate deposited on an oxide and silicon and SOI structure that absorbs incident infrared radiation and generate photo-induced carriers. This dial action enables dynamic adjustment of the device response. The optical signal from the germanium gate modulates the channel current, while the gate voltage fine-tunes the expansivity, dark current, and noise. Our first simulation gives EDS VGS characteristics with IR light power of 10 nanowatt and with dark. The red one is with 10 nanowatt power light, and the dark one is with dark. I mean, it shows that the drain current is increased when the gate voltage is more than minus 0.5. These findings confirm that the device operates as a gate-tunable phototransistor, where gate modulation exerts strong influence on photocurrent extraction efficiency. Such behavior is desirable for optoelectronic switching and highly sensitive photodetectors application. Another curve, it presents the responsivity versus the germanium gate doping concentration of the investigated junctionless phototransistor device with doping values and VGS and P, as shown in this. As the germanium gate doping concentration increased, the device current under IR illumination reduced, as shown in the curve. This in turn induced degraded IR responsivity because of a higher work function creates a more substantial barrier to carrier through within the silicon channel, limiting the overall modulation of the channel conductivity. The deep, we move to the deep learning modeling and analysis of the phototransistor properties. The deep learning classification approaches offer a potential pathway to predict and explore the impact of various design parameters on the junctionless phototransistor IR, photoresponse, and noise characteristic, which will be investigated in the next section of cost structures. Analyze a data set comprising 324 samples characterized by 4 input features and 1 output variable. The input features include gate doping concentration, channel doping concentration, oxide thickness, and silicon thickness. The contribution will benefit of positioning and highlighting this new approach in comparison with previous published work. So the first figure, it's a summary of a data set K feature and output variable distribution. This figure illustrates that for oxide thickness, it's stable, but for the other values, input values, distribution of gate doping, distribution of channel doping, and distribution of silicon thickness, the output is varied in function of the count of simulation. Then this is summarized in this table. It summarizes statics count, means, standard, minimum, quaternions, and max for input features and responsivity. for the gate doping as an input, channel doping as an input, oxide thickness as an input, silicon thickness as an input, and the output variable is the responsivity. The count are free, as I said before, is 324 for all inputs and outputs. So we see the responsivity values, how they changes from min values to max values in relation with the input the input. So we have created a three model. Model 1 with 2 layers, model 2 with 3 layers, and model 3 with 4 layers, and model 1 with 3216 neurons. The model 2 is with 64 3216 neurons, and 128 64 32 and 16 neurons for the model 3. And we have in this table electrical comparison of model performance. I mean comparison between model 1, model 2, and model 3 values of R and root mean error. Yeah, RMSE. 3 deep neural network architecture with increasing complexity were designed and trained to predict the output variable. Yes, the responsivity based on the 4 input features we have mentioned in the before. Then we have a figure which presents shape feature values impact on model output. And on this figure, the results reveal that channel doping, this one, channel doping, and silicon thickness are the most influential parameters driving the model's output, with the main absolute shape values of approximately 328.7 and 258.2 respectively, as it is shown here. So we conclude our study that it's we have seen here that this study has comprehensively examined the influence of key design parameters on the performance of the junctionless phototransistor infrared. The results show that optimized doping and bias conditions yield a high responsivity with a reduced dark current. They reveal key design parameters that significantly impact phototransistor efficiency and provide valuable insights for optimizing device design. These findings highlight that the synergy between device physics and GL-based modeling provides a powerful methodology for the design of next generation low power, low cost, and high performance junctionless phototransistors for inter-chip data communication application. Thank you, and I would love to hear your thoughts or questions. Thank you so much.
Some question, some observation from the audience. No? Okay, if no, I have one question, Rabia. Could you put a figure 2, please? Figure 2.
Yeah, I will.
So you are doing a gate modulation with applying a voltage in a gate.
This
So,
one, yeah.
okay. So, but in your case, this is infrared detector. So how do you relate this gate voltage with infrared detection system? I couldn't understand this issue. You can understand what I am asking?
Yes. Okay. It's a simulation done with Silvaco, and we have a framework in Silvaco in which we can add infrared light. And yeah, when we simulate without, we don't add infrared light. And when we add it for dark, we don't add it as in the script. And with it, we add illumination, and with this power 10 nanowatt. Yes, it's done in Silvaco. Yeah, Silvaco.
Okay. So this 10 nanowatts of infrared power is, I to say, that is equivalent for a gate voltage in this case.
Oh, yeah.
Okay.
Yeah.
Okay, thank you.
You're welcome.
So some other question of that? Okay, thank you very much for your presentation.
You're welcome.
So also you are going to continue with your presentation?
Yes, if you
Okay,
if
so
I can.
okay, so the next is low power design of a 3 gigabytes per second LVDS receiver for optical data transmission. Okay, so please start, Rabia.
Yeah, thank you so much. And it is clear for you, yeah? It's no
Yes.
problem with sharing.
Yes.
Yeah, okay.
Go
Thank you.
ahead.
Okay, thank you. Then we will continue with my second paper entitled Low Power Design of a 3 Gigabit LVDS Receiver for Optical Data Transmission. Yeah, we will start, of course, with an introduction and background, and then the modeling low voltage, low power LVDS receiver simulation result, and we conclude by a conclusion. Yeah, the idea of this paper is to write with many electron beams in parallel and then achieve a reasonable wafer through output. And this is for deep submicron chip production. How can we achieve that? So we have our system showed in this figure, a maskless lithography system, PML2 tool, for the 45 nanometer and 32 nanometer node and beyond. And it's clear that there is an aperture plate on this level in the system, and it's contain all famous electronics. It is a system with 200 reduction projection optics where patterns are generated on 300 millimeter substrates using a programmable aperture plate system, APS, this one, with at that level, with integrated CMOS electronics, generating several thousands of well-defined electron beams in parallel. So the idea of raising mask, it costs chip production, and then it requires to minimize the cost, the mask, the rising mask cost. It requires projection maskless lithography system, which includes the aperture plates. The aperture plates have electronics on it, And then there we will find the DMUX1 chip, our chip we have designed and fabricated with the low voltage differential signaling receiver. The low voltage signaling differential signal LVDS receiver, the main block in it is a comparator and an adaptable delay check. The logical data path diagram of this system is presented in this figure. We see at the input an optical receiver with 36 optical channels at 1 gigabit. And then the output of the optical receiver are presented at the DMUX1 chip. We have 4 DMUX1 chip and with 36 LVDS channels at 1 gigabit, including, of course, 4 common control channels. The output of these DMUX1 chips are transmitted to another DMUX chip, but it's DMUX2, not the same one as this chip. And then the outputs of the DMUX2 are oriented to the deflector electrodes. So about 20,000 to 25,000 aperture deflector electrodes at 40 kilohertz to 1 megahertz. This is the logical part of the system. The LVDS receiver represents the main critical parts in the chip, since they are analog, and since there are 12 copies of them in every DMUX1 chip. And it is also their responsibility to supply the digital part with adequate signal. And also we have 4 DMUX1 times 12 system, and this is why this chip is have a main function. So the block diagram of the receiver presents a 3 block. The first input block is a different comparator, and then an amplifier and buffer to amplify the single-ended signal coming from the comparator, and then the adjustable delay chain to where then the output is directed to the DMUX2, as we have presented in the obvious figure. Then, simulation result of the LVDS receiver presents here in this figure. The input signal is in A0 and in B0. It's a sine wave with 50 millivolt amplitude and 1.5 gigahertz frequency. The output of the comparator is here, CMP2, and it shows how the comparator block is reacted, and the last signal, this one is the output of the LVDS receiver whole block. It shows that it responds to the variation of the input voltage, differential input voltage. So this LVDS receiver is its layout is presented here, LVDS receiver layout style. So this is the amplifier and the comparator, and of course the two pads with ESD protection. And we have, as we said, and as you mentioned, 12 of this LVDS receiver in the chip, in one chip, and in the whole aperture plate we have 48 LVDS receiver. A comparison table is presented in this slide. LVDS of LVDS receiver, we see that our result is 3.5 milliwatt power consumption at 3 gigabit and 1.8 watt. For a paper reference has 18 nanometer, sorry, but they have used fine FET and not a CMOS FET. Yes, fine FET, I mean another kind of transistor. Data rate, they reached 5 gigabit with 1.2 milliwatt power consumption for 2.4 power supply, input output power supply. The other paper, the other result is also 18 nanometer, also a fine FET with 3.2 gigabit and 6.8 milliwatt with 1.8 volt. Then they use the same as we have used 1.8 volt power supply. The third result is 150 nanometer CMOS, and the data rate is 2 gigabit. Power consumption is 3.5 milliwatt, and yeah, they have used the 5 picofarad load. Those results, we have compared our result to it. So in conclusion, we have the proposed design was implemented using 180 nanometer UMC CMOS technology, specifically optimized for optical application. The DMX1 chip is capable of recovering data signals at data rate ranging from 1 gigabit to 3 gigabit. Compared to conventional design, the proposed LVDS receiver architecture offers significant improvement in circuit complexity, layout, area, and power consumption, making it perfect for optical data transmission application. So, thank you so much for your attention, and yeah, thank you.
Okay, thank you for your presentation.
You're welcome. Thank you.
Some question, doubt on the presentation from the audience. Are there some questions or that? We have enough time, probably almost 10 minutes for discussion. Okay, Rabia, I have one question. In a table 1, you are giving different parameters for different performance of a FinFET and CMOS. So this is it's a simulation of your receivers in this case. Which kind of simulation you did here? Okay, it's a different author.
Yeah. You mean simulation to have those results?
Okay. You are giving presentation of 18 nanometer FinFET. There are two types, and the last one is 150 nanometer CMOS. So all of them is simulated data, or there are some experimental data.
Okay. They have experimental data, and we also have experimental data, but it's not presented in this paper. That's it. Yeah.
Okay. In that sense, what is the main difference between both the same 18 nanometer FinFET, because they have a different power consumption, and what could be the difference of what you are giving to understand the difference between those FinFET?
They didn't use the same power supply. This one they have used the 2.4 volt input output, and they reached 5 gigabit data rate. And the second one, they have used 1.8 volt power supply, and they reached only 3.2. And this is in 2022 year, and this is much recent, 2024. The first one, yeah. But it's but it's with more power supply. I mean, it's 2.4 and not 1.8. Then the design, it's perhaps the main difference in the design. They improve the design.
Okay,
yes,
but
because
okay, in this case, it's a 2.4 volt, which is greater than the 1.8, but that is consuming this power, only 1.2 milliwatt.
Yes, yeah. This is this improves that they improve the development, the design, because it's the same technology node, but the design it will not be the same. It's a different design.
Okay, thank you.
You're
Question
welcome.
from the audience. We have still 5 more minutes. Ravia, I wanted to ask you. You are from the University of Patna.
Yes.
Patna University.
Patna University.
In which country city are located?
Algeria, from Algeria.
Okay. In which city?
Which city is Patna city? It's in
okay.
east of Algeria.
Okay, thank you.
Yes, you're welcome.
Questions? Okay, so probably there are no more questions. So thank you very much for your presentation.
You're welcome. Thank you. You're welcome. Thank you so much for everyone.
To prepare the next speaker, Maylu Guadalupe Romero, Omar Rodríguez, José Manuel Juárez, Alondra Ana y Ortiz, Olaf Martínez, and Diego Castillo. Development of solar panel monitoring system for power and visible light using Arduino and INA 219 BH1750 sensors. I know the speaker is Olaf Martinez. Olaf, is you are there in the online?
Hi, hello.
Okay, so please prepare your presentation. Olaf, could you please mention which institution are you? Okay.
Good afternoon. I'm from Universidad Politécnica de Querétaro.
Okay, thank you. So probably 2 or 3 more minutes, but in order to save the time, probably we can start with your presentation. Please, Olaf.
Could you please give me 1 minute? I can see my screen.
Okay. Yes, of course.
Thank you. I'm ready.
Your presentation. Okay.
Yes, now that's okay. So,
So,
can I start?
Olaf, are you ready?
Yes, I'm ready.
Okay, please start your presentation.
Well, again, good afternoon, ladies and gentlemen, esteemed colleagues and members of the CCE organizing committee. My name is Olaf Martinez Guzman from the Universidad Politécnica de Querétaro, and I'm honored to present our research in the solid-state materials, electron devices, and integrated circuit station. Our paper is titled Development of a Solar Panel Monitoring System for Power and Visible Light using Arduino and the sensors INA 219 and the BH 1750. Starting, we'll talk about the motivation. Motivation for this project is anchored in the persistent need for tools to study and analyze photovoltaic performance. The high cost and restricted access to professional parameters limit practical research, and we focus on education. Our first objective was to address this gap by developing and validating a system that is both functional and economically viable, capable of monitoring the key parameters of electrical power and visible light. As I said, the focus of this research was the technical validation to a low-cost system with low-cost components and that can provide reliable data and validate that evidence that solar trends and establish a correlation with the electrical output. So this slide illustrates the architecture. In the right side, we have the diagram, which is built around the Arduino Uno microcontroller, and the data flow is handled by two main I2C sensors, the BH1750, which is used for measuring the visible light in lux, the sensor INA219, which is measuring electrical parameters, voltage and current, and the microcontroller, also the photovoltaic panel. Our technical challenge was the conversion from lux to irradiance. In the equation 1, we see that the formula uses a 116 factor, which is the empirical constant used to perform this conversion under assumed standard in their mass conditions. Our target is E, which is the estimated solar irradiance represented in watts over square meter, and L is the measured illuminance in lux given by the sensor. Our methodology follows 3 stages. First, the validation, then the systematic data acquisition, and the final calculation of the efficiency. We have the efficiency formula, which is equation 7, that defines the power output, the electrical output, and the incident solar power. First, the P out means the voltage and current readings acquired using the INA sensor, and the P in is calculated by the estimated irradiance and multiplying it by the effective area of the panel. This framework ensures that our efficiency determination is fully traceable to our low-cost measurements. Beginning with the results section, the first step was validating the pH sensor. In figure 3, we made a linear regression and compares readings from our low-cost sensor against a professional reference lux meter across the operational range. The result is outstanding. The coefficient R² is 0.991, confirms the excellent linearity and minimal systematic error in its response to visible light, validating the sensor as high fidelity for our input. And on the right side, we have table 1, which summarizes the absolute and relative errors during calibration. The error metrics reinforce the sensor's acceptable real-world performance, making it highly suitable for the proposed application. Sorry. We have the second result, which is the figure 4, represents a time series record showing both the estimated irradiance and the generated electrical power measured over a typical period. You can see in both curves track the expected daily solar variability. The irradiance curve derived from conversion, which is given from conversion, mirrors the natural solar profile, and the power output follows this trend directly. This correlation confirms that the system ability to consistently measure and track the dynamic variation of solar input and the corresponding electrical output in real time. This slide proof of concept our empirical model in figure 5, which is on our left slide. We have a scatter plot relating the estimated irradiance of the x-axis to generated electrical power on the y-axis. The relationship is clearly linear and strongly positive. The regression analysis yielded a coefficient of determination R² of around 0.086. There's a mistake there. This indicates that 86% of the variation in the generated power can be statistically explained by the variation in our estimated irradiance. These results successfully validates two critical points. First, the effectiveness of the conversion, and that a low-cost system provides a reliable and predictive model for the panel's electrical performance. Finally, our sixth figure shows the instantaneous panel efficiency, calculated over time using the equation 7, which is the efficiency formula. The calculated efficiency values remain realistic in the small solar panel under test, ranging approximately between 7 and 13%. The fluctuations observed are expected due to varying cell temperature and atmospheric conditions. The fact that the calculated efficiency falls within this physically plausible range confirms that the overall efficiency of our integrated system and the reliability of our methodology. In the discussion, we address the system's primary limitation. The overall measurement uncertainty is estimated to be plus or minus 20%. This deviation is directly attributable to the use of empirical loss to irradiance conversion, which is the 116 factor. This cannot compensate the continuous changes in the solar spectral content throughout the day. This 20% margin is necessary for trade-off for the massive cost reduction. For this application, which is laboratories and academic purposes, is highly sufficient and provides significant utility where high-end instruments are unavailable. The value proposition of this system is centered on accessibility and replicability. First is a key educational tool, providing hands-on experience in sensor integration and photovoltaic analysis for institutions with limited budgets. Then, its foundation on open hardware systems ensures it is fully replicable globally, fostering collaborative research and experimentation. Finally, the system provides sufficient data quality for monitoring and comparing the relative efficiencies and trends of different solar devices. To conclude our presentation, first, we successfully developed and validated a cost-effective and highly replicable solar monitoring system using the Arduino platform. Second, our core validation demonstrated a strong positive correlation, R-squared around 0.86, between estimated irradiance and generated power. Third, the system is a viable and highly valuable tool for both analyzing performance trends and supporting solar energy education. Our future work is focused on maximizing the system's utility and accuracy. We will integrate wireless communication, moving the systems toward an IoT solution for remote monitoring. Crucially, we plan to explore the use of multispectral light sensors to refine the accuracy of our irradiance calculation and reduce the system uncertainty. Finally, we will develop a graphical interface to get the real-time data visualization for the end user. Well, thank you very much for your valuable time and attention. I would like to acknowledge the collaborative efforts of my co-authors and the support from the Universidad Politécnica de Querétaro. I'm now open to any questions you might have regarding this research.
Okay, thank you for that presentation. So the presentation is open for discussion, comments, question, doubt. Everything is clear? Okay, please.
Hello, lab. First of all, I want to thank you your neat presentation. It was very clear. I just want to say a comment. If you use, the comment is that if you use an Arduino controller, so for monitoring, when you have to monitor like big measurements, like you put this, you wanted to monitor up to 20,000 luxes or something like that. The Arduino resolution it won't be enough. The rest of the Arduino has like 7, I think that's 7 bits, 8 bits. I don't remember, but when you have to measure a big range of a physical measurement, Arduino is always get short. Well, it only serves for a limited range of measurements. So I advise you to get a better resolution electronic board, because if you don't do that, you never get the accuracy that you are looking for. That's my comment.
Yes, I think actually in the university we are developing a new system, which is, I think I said that in the IoT, Internet of Things, and have a better microcontroller, which allow us to get a lot of get a better range of lux measurement. Also, we have a computer plugged into the Arduino the whole time of the reading. This is not efficient, and well, first we have to stay in the budget that we have, so stay low cost possible.
Okay, thank you.
So that question, please.
Well, it would be good to have idea of the nominal efficiency of the module. What the provider of the module gives you as the efficiency. You say that you measure the efficiency and you get a variation between 7 and 13%. So it would be interesting what is the nominal efficiency.
Well, yes, it would be better to have the nominal efficiency, but we use a very simple equation and not have.
No. But the provider, I suppose that you are using a commercial module, no?
Sorry, I can understand.
You are using a commercial-based photovoltaic module.
Yes.
Yeah, and the provider of the module tells you under normalized conditions, you have this efficiency. What is the nominal efficiency?
I can't remember right now, but I think we use like 2 or 3 panels, and they were from different supplies.
Okay. You have to have this information in order to compare what you are obtaining as a result. Okay.
It was like
because
50%.
the average efficiency of your measurements is about 10%. And so what's the nominal efficiency, which is measured under normalized conditions. And in that way, we can evaluate how good or why, the question is why you would obtain a different efficiency, average efficiency, as compared to the nominal commercial efficiency.
This was a commercial solar panel. It was 13%. The nominal efficiency. It was for didactic use. 13%.
Yeah, this is important information because you are using them in the average 3%. And this is information important when you want to calculate the use of these modules in the practice. Okay, thank you.
Well, thank you. Appreciate it.
More questions, comments? Yes, Olaf, this is just Hiro Matsumoto. The observation of a photovoltaic module efficiency, I think, is important. The fluctuation you show from 7 to 13%, it is happening, something wrong. So you have to rectify and to check what is happening because that fluctuation, you know, because the efficiency may not change so big.
Las que están midiendo en condiciones reales y las condiciones están cambiando.
Sí, correcto. La entrada y la salida.
Sí, la eficiencia no puede ser igual.
Okay, thank you, Olaf, for your presentation.
Can hear very well, but thank you.
So next speaker, Roshini Ravi, Govan Kumar Paner, and Maria de Luz Olvera. The title of the presentation, silver added as thin dioxide coatings processed by Soldier, deep coating for carbon oxide and propane gas sensing. So the speaker is Roshin. So probably we have still 1 more minute.
Yeah,
Sobre la
that's it.
estamos pagando luces con mariachis.
Sí,
No es eso.
pero sí puede estar la misma.
Ramik.
Yeah.
Thank you.
Okay. Let me begin with the motivation of this research, understanding the critical issue of air pollution. To understand air pollution, it is essential because we have to address human health, environmental safety, and mitigating climatic changes. These air pollutions have various sources, and the major contribution is from industries, agriculture, and transportation. When we talk about air pollutants, there are several harmful substances, including toxic gases. In this study, we refer two such toxic gases, carbon monoxide and propane. Carbon monoxide is a health risk, colorless and odorless gas, which is capable of causing severe health issues in humans, especially which can also lead to death. On the other hand, propane is a widely used flammable gas which has high risk of explosion, especially in the enclosed spaces. Therefore, development of effective, reliable, and high sensitive performing gas sensor is a paramount objective to ensure the safety of the environment. This brings us to the most researched semiconducting material for gas sensor, that is tin oxide. Tin oxide is an N-type semiconductor which has high electrical conductivity and optical transparency. This intrinsic properties of tin oxide make them more efficient in the use of gas sensing application for various toxic gases. However, there are some of the shortcomings that are needed to be addressed, such as their slow response time and their poor selectivity to multiple gases and their stability in the harsh environment. Researchers are focusing on to sort out this problem, which would make this tin oxide more efficient. This research focused to enhance the performance of the tin oxide with the addition of silver. We hypothesize that addition of Ag into tin oxide matrix would enhance their surface active sites, which increases the oxygen vacancy and hence would enhance the performance of the gas sensor. The objective of this research is to first synthesis Ag-ADA tin oxide coatings. Second, to evaluate how different Ag configuration in the tin oxide matrix affects the structural, optical, and morphological characteristics. And third, to perform the gas sensing of two different gases, carbon monoxide and propane. Finally, our aim is to identify the optimal Ag layer which shows highest response for both the gases. Part 2 is experimental section. Here I talk about the synthesis we did and the characterization techniques we used. The synthesis of Ag-ADA tin oxide coatings is divided into two parts. Part 1 is making of tin oxide coatings and part 2 is the addition of Ag into tin oxide coating. Part 1 was referred to an article which is already published, and it was confirmed that the 3 immersed tin oxide coatings showed maximum sensitivity for this application. On the other hand, to do the part 2, we added 0.39 grams of silver nitrate in the 100 ml of methanol solution. This solution was used to dip the silver tin oxide coatings at 1, 2, and 3 layer, depending upon the immersion times, which is 1, 2, and 3. So this dipping time for each immersion is 45 seconds, and after each immersion, these coatings were dried at 200 degrees Celsius for 5 minutes. Once all the coatings with all the 3 immersions were made, these coatings were annealed at a temperature of 450 degrees Celsius for an hour. After annealing, these coatings were slowly cooled at room temperature. Once all the coatings are in hand, we did the characterization techniques to know its structural analysis, which was done with XRD, and to know the morphology of the films, we studied SEM analysis. And AFM helped us to use the study the nanoscale topography of the film, and UV-Vis on the other hand helped us to know the optical transmittance and band gap changing. Once all the characterization was done, these materials were used for gas sensing measurement, where the homemade setup was used, which had the equipment involved gas inlet valves and 2 tanks of gases, that is carbon monoxide and propane, and low resistance multimeter, and temperature and pressure controller, and silver paint, which acts as an electrode. Once the measurement was taken, the calculation for sensitivity was done within a formula which is R0 minus Rg by R0, where R0 and Rg are resistance in air and resistance in gas, respectively. Part 3 is result and discussion. Starting with the results and discussion, let me begin with structural analysis. The structural analysis was done with XRD, where all the X-ray diffraction patterns of Ag added tin oxide showed and confirmed the tetragonal rutile phase of tin oxide. Interestingly, there was no secondary phase of Ag formed, which confirms that successful addition of Ag into tin oxide matrix. On the other hand, we have to observe that there's a trend in decrease of crystalline size with the addition of Ag layer, and the lattice parameter showed slight variation, which is almost negligible. So this lattice distortion and defect formation in this form may or can lead to change in the surface active sites and electronic properties of the film, which can affect gas sensing performance of the material, because these are two key factors for gas sensing. Scanning electron microscopic images visually confirms the impact of Ag on the film morphology. Interestingly, we have to notice that increase in the addition of Ag layer has enhanced the nucleation and growth, which affected the size and the porosity. For example, early coatings like the layer 1 showed finer grains and initial porous structure, whereas the later coating, especially the 3 layer 1, showed interconnected larger grains which had more porous structure than the initial ones. These change in porous structure, surface area can again affect the properties of the film structure, which may lead to change in the gas sensing performance of the films. Moving on with the UV spectroscopy analysis, where all the Ag added tin oxide coating showed high transmittance in visible range, where it was maximum about 70%. And we have to note that this material can be used and it's suitable for the application that requires transparent conductive oxides. And we can find the slight variation in the band gap of with the addition of Ag, which confirm the change in the electronic structure of the material with increasing Ag content. And also the change in band gap can lead to change in the gas sensing performance of all the films, since it is a chemical assisted gas sensor. It's mandatory. AFF analysis gives us the quantitative data of surface roughness and grain size. Here, in this case, we have to note a trend that the average roughness of all the films tend to decrease with the increase of addition in Ag layer. On the other hand, average grain size follows the same trend, where addition of Ag content decreases the grain size too. And from this results, we analyze that the 3-layer Ag added tin oxide coatings, we have 3 immersion of Ag, shows a smaller grain size and smaller average roughness. Moving on to the gas sensing measurements, which are the application of this part. This is where all the structural enhancements so far discussed shows their value. First, let us discuss the gas sensing measurement for carbon monoxide gas. Here, from the graph, we can illustrate that the sensitivity depends highly on operating temperature and the addition of silver layer 2 in this case. We can see that the 3-layer immersed Ag tin oxide coatings show a maximum higher sensitivity, which is very significant. At an operating temperature of 300 degrees Celsius and at a concentration of 500 ppm, we get to calculate that the sensitivity of 3-layer immersed Ag tin oxide coating shows approximate value of 547. This is very high compared to other 2 films, where it should be noted, and it should be noted. And moving on to the measurements of propane. Here, when we talk about the propane gas sensing, we see a similar trend followed by carbon monoxide for the films. Here, this also depicts that the sensitivity depends on the markedly increase of Ag content and the operating temperature. We can notice that again the 3 immersion Ag added tin oxide coatings showed a highly markable maximum response for the gas. We can see that at the concentration of 500 ppm at operating temperature of 300 degrees Celsius, the 3-layer immersion of Ag added tin oxide coating showed maximum sensitivity of 876, which is highly significant when compared to the other two films. So we are concluding all the results we saw so far. We conclude that this work significantly demonstrates how enhancement of the film happens with the addition of silver structurally and also in the application performance. The comprehensive characterization of the films like structural, morphological, and optical characteristics shows how each immersion of Ag influences the structure's morphology. Finally, we conclude the point that the 3-layer Ag added tin oxide coating showed maximum sensitivity at higher operating temperature, which is 300 degrees Celsius for both the gases, which is 547 for carbon monoxide and 876 for propane. However, we have to address some of the questions like pore size, density, and film thickness changing with the addition of Ag to know the gas sensing mechanism in depth, which would be addressed in our future work. This work was conducted and built upon strong foundation of already existing work, which are listed here as references. We are grateful for the funding support from CONACYT and for the various departments in Sinveta, which helped us for characterization. Thank you all for your attention, and I'm happy to answer your questions now.
Thank you for your presentation. Question, doubt for the audience? Nothing? About 5 minutes?
I didn't see the reference that I mean, without the silver, you thin oxide layer without any silver.
Actually, it was reported in another article, but in that article, the sensitivity was done for the films and pellet. In both the cases, the sensitivity was about from 40 to 80, which is in this case 10 to 15x higher than the response of that. It's not mentioned here, but it's in the reference list.
But you did the measurements for pure thin oxide?
Not in this work, but it has already been published in some other work.
Somebody.
Yeah, not.
You need your
No,
your own results.
not in this work.
Yeah. Okay. That's missing. Okay, so that you can compare your own layers with silver and without silver.
Okay.
One question regarding sensitivity. Do you know the data for commercialized gas sensors for a propane or for a carbon monoxide? What is you detected 500 ppms at 300 degrees,
Yeah.
but correlated the common conventional sensor. What is the value?
In commercial sensors, we find a trend that this operating temperature is far more higher when compared to that because as in practical need, we have to sense this gas at early temperature and at early concentration to avoid higher risk at the higher concentration and temperature. The commercial sensor has already reported at early room temperature sensors and also at 20 to 50 ppm at low, which has lowest detection limit. So industrially, there are far more better, but this needed to be addressed to be used in industry phase.
Okay, so the better sensor is at a lower temperature and high more or more sensitive in this case.
Yes.
Starting in the tens of ppms. Okay.
Yes.
Okay. Thank you. Question? Objection? Okay, thank you very much.
Thank you.
For the next speaker, probably again Rabia Ocean, Quaker Jeffal. This is again from the University of Varna in Algeria.
Yes.
The title is a performance analysis of a sub-threshold differential amplifier using JLGAA, Verilog A, behavioral modeling, and device level DG model. So could you please prepare your presentation, Rabia?
Yes, of course. Um,
So please, Rabia, please start.
okay, thank you so much. Then, hello everyone again, and we will see together our presentation entitled Performance Analysis of a Sub-threshold Differential Amplifier using Junctionless GAV Verilog A Behavior Modeling and Device Level Gate Model. Then our presentation outlines our introduction, device structure, and design. Then we know that a wearable health monitor to implantable neural recording system are required continuous signal acquisition and also processing and transmission. All this thanks with low power gives patients safety and extend device durability. To the most used device in that kind of systems is a voltage amplifiers, and it plays accurately capturing weak biomedical signal. So the challenge in that kind of device, challenges in voltage amplifier design, is the most important one is the power consumption. So, and of course, the noise performance and the physical size. All that challenges, the solution for them is to use a sub-threshold circuit design, which enables an ultra-low power operation, which is needed in biomedical application. The challenges in sub-threshold nanoscale CMOS amplifier design is a process variation. Those kind of device are highly sensitive to process variation, and which means noise and also temperature fluctuation. Here, the solution is sub-threshold circuit, and of course, which enable ultra-low power operation. The development of in our work, the development of a compact Verilog A junctionless GA transistor model is employed. So it is we have done an implementation of a fully sub-threshold differential amplifier, and this implementation satisfies the string specification for power delay, product minimization, high transconductance to power efficiency, and integrity preservation of a fully sub-threshold differential amplifier. This is highly suitable for ultra-low power nano-electric complex circuit also. So we move on to the device structure and the design methodology. So the figure 1 presents a three-dimensional view of the junctionless GA FET. The 3D structure of the analyzed nanoscale junctionless GA FET device technology node. The device was doped using uniform doping concentration profile. The gate length L is fixed at 10 nano, while the gate oxide is 0.5 is considered with junctionless structure, for which the channel region is considered N plus type uniformly doped here. Our first figure of simulation figure, is a drain current ID versus drain current ED versus gate source voltage VGA. The result in this curve below confirms the superior electrostatic control of the GA structure, making it highly suitable for ultra-scaled low-power applications in advanced technology node. Another curve is the output characteristics, EDS versus VDS at VGS equal 0.4 volt for the GA transistor. The ultra-low current level result that confirms that the device is operating deep in the sub-threshold region, emphasizing the strong electrostatic control and junctionless GA transistors. These characteristics are particularly valuable in low power and high density. We move to the use of our Verilog model in amplifier, differential amplifier design. This is a schematic of our design using our model, my GL guy here. So those two transistors, Verilog model transistors, are the input stage of the differential amplifier. We have tested our design. The first curve is gain versus frequency response of differential. We have tested it using cadence specters. This is the curve. It's present the gain versus frequency response of the differential amplifier operating in sub-threshold region. This behavior is consistent with the expected performance of a sub-threshold inverting amplifier, where the transistors operate in the weak inversion region. resulting in low transconductance and limited gain. The next simulation result is about temperature stability of gain in junctionless gap-based differential amplifier. It's clear that this minimal sensitivity to temperature confirms the amplifier's strong thermal robustness, a crucial feature for biomedical systems that must operate reliably in various physiological and environmental conditions. We have summarized different simulations in this table. We have a frequency dependence of differential gain, a common gain, and common gain ejection ratio in a GL-based subspecial differential amplifier. This table presents the variation of RDM, RCM, CMMR in relation with frequency from 10 Hz to 100 megahertz. Of course, the design based on our model designed in Verilog A. Then comparative parameters with the existing work is shown here in this table. Then our GLGA design with power supply voltage of 3.3 volt, bandwidth 1 Hz to 100 megahertz, and maximum differential gain of 66, and then CMMR of 44.91. The previous topology have 5 volt as power supply voltage, 1 megahertz as bandwidth, and then 6 decibel of frequency gain of frequency between 10 and 1 mega, and CMMR common mode rejection ratio of 33.96 for the mentioned bandwidth, of course. The GLGA design demonstrates better power efficiency and compatibility with low voltage modern systems. It shows a significantly wider bandwidth up to 100 megahertz, enhancing performance for high frequency applications. And we conclude that the proposed GLGA design demonstrates significant improvement in gain, bandwidth, CMR at a low supply voltage, indicating superior small signal performance, making it a more efficient and robust design for modern integrated low power systems. This study bridges the gap between device level physics and circuit level design, providing a comprehensive co-design methodology. The presented modeling and simulation framework offers valuable insights and design guidelines for researchers and IC designers developing next generation analog and radio frequency circuit using beyond the CMOS technology. Thank you so much for your attention, and please kindly questions or remarks. Thank you.
Okay, thank you, Rabia, for your presentation.
Yeah,
Thank you. Now that this presentation is open for discussion, some questions, doubt from the audience. The audience. We have still 8 minutes for discussion.
No.
I have one question, Rabia. This is Yasuhiro Matsumoto.
Yeah.
You gave the you are considering very thin oxide. You mentioned 0.5 nanometers. That is a 5 angstroms. normally in this kind of design, I'm not sure, is using this kind of thickness of oxide. How they are controlling this thickness?
Sorry, but can you repeat? Yeah. How we control of the oxide? How we control the oxide thickness? This is your question?
Yes. Okay. One of the question is if really they are considering in the design or a simulation 0.5 nanometers nowadays, and if we really are how they are depositing this kind of oxides.
It's a script write it in Silvaco, and you can use Atlas to create the structure and then simulate with Silvaco too. Yeah, the simulator of Silvaco. Yeah, because we have created first the design in Silvaco, and then we created the Verilog A model and bring it to Cadence. And then in Cadence also you can change thickness, oxide thickness in the Verilog script, Verilog A script.
Yes,
You
but
can
in
do it.
But in the practice for doing this kind of a device, probably 10 nanometers gate length is possible, but I don't know what is the minimum amount as a gate length or oxide thickness, which is available for a real device. Do you know?
A real device.
Yes.
Okay. For the GL gas structure, it's not, there is no really experiment design for this structure. The researchers are still testing it and trying to go to a good design, I mean. But in real design, real transistor, it's not yet an experiment transistor with that kind of structure. Even it is so simple as the other structure, because we have a junction left, so it's more, the process is more simple. But still, we don't have experiment like that. Yeah, it's the simulation, and it's our objective is also to go forward to Verilog modeling. Yeah.
Thank you.
Yeah, welcome.
Comments, questions, no more? Okay, thank you very much for your presentation, Flavia. Jose.
Yeah, welcome. Thank you. You're welcome.
So let's move to the last today's presentation. It's given by Marisela Meneses, Mario Moreno, and Ramon Ramos, Yasuhiro Matsumoto, Miguel Zarate, and Federico Ramirez. The title is Study of Silicon Oxycarbide Films Deposited by CAT-CVD using methyl-3-methoxysilane for application in optoelectronics. So the Marisela is the presenter. Okay, so please
Yes.
go ahead.
And thank you for presentation. I talk about a study of oxycarbonyl silicon films deposit for catalytic chemical vapor deposition using methyl-toxicilano for application in optoelectronics. The content of this presentation is introduction, objectives, experimental part, result and discussion, conclusion, and reference. Well, when introduction, the silicons is a powerful technology for integration optical function and on the same chip. For example, one application is for data transfer with light. It's important obtain emitting, transfer, and detector based in silicon. However, it's necessary obtain light emitting diode based in material of silicon. There are different materials. For example, silicon-rich silicon oxide, silicon nanocrystal in silicon oxide matrix, silicon nitride, amorphic silicon carbide, oxycarbyl silicon that are compatible with CMOS technology. For example, in this part, we show some characteristics respect oxycarbon silicon with nanocrystal in oxycarbon and nanocrystal in oxide matrix. Oxycarbon silicon is possible obtain a low temperature, present low constant dielectric, present high thermal and mechanical stability. It's possible obtain optical band gap, wide optical band gap, and it's possible obtain emission visible. In the other hand, nanocrystal silicon is necessary high temperature for deposition. Additionality is necessary high temperature, but present high thermal and mechanical stability is possible. The control of size of nanocrystal is possible. Obtain emission from blue to near infrared. However, oxycarbon silicon is a good material because it's possible obtain a low temperature. This is very important. However, this device present low efficiency. Then it's important to study some strategies to improve this efficiency. There are incorporation or aerobio nanocrystal silicons or incorporation with metallic elements. Oxycarbon silicon is possible obtain the different methods. For example, chemical vapor deposition, plasma enhanced CVD, hot wire CVD or catalytic chemical vapor deposition, sputtering, and the others. Some advantage, for example, present simple configuration is low cost in comparison to the other CVD. It's possible to obtain high deposition rate, present high quality films, and it's very important, it's possible compatible with organic and inorganic precursors. However, present a very important disadvantage. And this disadvantage is the incorporation of the filament substrate. This probability which might introduce some defects. Objectives work. Obtain and investigate optical structure and morphological properties of silicon films. Deposit using methyltoxicity and MTMS. Analyze the impact of thermal aligned at 500 degrees Celsius, 700 degrees Celsius, and 800 degrees Celsius on the film properties. Develop a structure for electroluminescent devices. And this bar shows the system we used. The films were deposited on 5 silicon substrates with 1 to 5 ohms centimeters. wind chamber 0.3 torrs, empty and flow 0.5 SSCM, subtract temperature 200 degrees Celsius, tungsten filament 1,500 degrees Celsius for 20 minutes. And the thermal treatment process in nitrogen was done. And then the film's characterization techniques were photoluminescence, Fourier transform, infrared, X-ray, photoelectron spectroscopy, scanning electron microscopy, and atomic force microscopy, device fabrication. This device was so I need last well the device fabrication it was the active layer deposition is very important because in this layer it are the process the recombination. Then was deposited the back contact. Next, the top contact was deposited by sputtering, and the device was defined by photolithography used with activity area 0.0025 square centimeters. And electrical characterization of the device were EV emissions, electroluminescence spectra, and optical power. Well, photoluminescence results. In this picture, we can observe the intensity photoluminescence of as deposit with and arenal films. We can observe the intensity as deposit is comparable between the arenal film of 500 degrees Celsius. We'll use it 8, 6, 8, 8, and 7 at 800 degrees in great intensity at 2.8 electron volts. However, it is necessary the deconvolution to know the band, the position. In this graph, we can observe as deposit film and a linear film at 800 degrees Celsius. We can observe as deposit present two bands, one in at 3 electron volts and 2.24 electron volts, with a linear film present at 3.2 electron volts, 2.9 electron volts, 2 and 2.6 electron volts. We can observe that correspond violet, blue, and green emission. The blue emission is attributed silicon neutral oxygen vacants and carbon neutral oxygen vacants in oxycarbide silicon matrix. And green emission is attributed to silicon oxygen defect centers. Effective spectroscopy. In this part, we can observe the structure of the films. For example, as a positive film present 5 bands. These bonds, we can observe that are different as a positive with RNA film. We can observe two different. For example, one, this sheet this sheet of silicon oxide silicon is relation with the chain structure and increase this band. This band increase because the content of silicon increase. And additionality, the silicon oxide silicon appear at high temperature. And it's very important observe that this appear, this bond. Silicon relation with a hydrogen and carbon. Scanning electron microscopy. Well, in this part, we can observe the cross-section self-image of the positive film and adenal film. We can observe two important things. One, positive film is not uniform, not compact, and nanoporous. This would be incorporation of methyl and gray microvolts. Will the image of adenal film present uniform, compact, and reduce the porosity. However, it's probability there are present microvolts because remove OH and CH bonds during the thermal treatment could be at present microvolts or standing bonds. Atomic force microscopy. Well, in this part, we show morphology supervise of the fields. For example, in acid deposit, we can observe that present a robust at 9.6 nanometers, with adenal film present a robust 22 nanometers, and adenal films increase the robust because the agglomeration of nanoparticles increase. However, this value, 22.2 nanometers, is low robust. In the table 1, present the field properties, where we can observe when temperature decrease the thickness, refractive index change indicate the properties, optical properties change when the temperature aligned. XPL is necessary know atomic concentration of the each field. We can observe that there are present oxygen, carbon, silicon, and tungsten. In table 2, we can observe the atomic concentration at 30 nanometers of depth, where we can observe the carbon content decrease, oxygen increase, while tungsten content is high. However, this tungsten could be appear in tungsten trioxide. There are generic defects in the matrix of oxycarbon. Electrical characterization of the device. The device was forward bias polarization. We can observe the behavior current density, a voltage, and we can observe the device present diode-like behavior. In the other picture, we can observe optical power and time, where in this part, the optical power start detect, and maximum optical power is 3.5 nanowatts. Is lower yet. However, it's possible to obtain optical power. Spectra, electroluminescent spectra. In this feature, present three very important things. One, the device presents infrared electroluminescence, visible electroluminescence. Additionality, we can observe in, well, this spectra, electroluminescent spectra, present in broad spectrum. We can observe that near infrared emission is detected from 6 volts, and this increase to 14 volts. Well, the emission visible is in this direction. However, in this graph are present, and this emission visible could be relation with red and green, and are associated with silicon oxide deficient centers and neutral bridge oxyhole centers, and infrared electroluminescence are associated with defective levels. And in this picture, we show the band diagram of the device. And it's very important to know the conduction mechanism. There are different for this type of device. However, this mechanism, the space share limited conduction, was adjusted because present vibration characteristics this mechanism. This present vibration with this slope are adjusted. When conclusions, oxycarbonyl film were subsequent deposit used methyl trimethylcellulose because it's very important, because this material is no application in device electroluminescence. Oxycarbonyl film showed to have optical properties, show the terminal line, the photoluminescent intensity increases at 800 degrees due to activation of radioactive centers. The device demonstrates a broad spectrum, visible and near emission. The visible electroluminescence was attributed to silicon oxide deficient centers and whole bridge hole centers, where near electroluminescence was associated with the deep level states, and space share limited conduction was the transport of the carriers. And we demonstrate the potential of oxycarbonyl silicon film for photonics and optoelectronics application. I would like to take thank the society for scholarship, and then would like to thank the Denich, Miguel, Galvan, Norma, Rosa Maria, Georgina, Edmundo, and Lázaro Huerta Arcos for having some reference. Thank you for your attention.
Thank you. So, questions, doubt? Now, yes, no, yes. No questions? Please.
Can we see the photoluminescence results that we showed?
No.
No, no.
Okay. I think solution, the other people, the other time the characterization. Okay,
Okay, what you showed.
okay.
Yes. You mentioned that you have a convolution
Yes.
with 3 bands.
Yes.
But you only explained 2. What happened to the other?
Okay. In this case, the blue and violet emission, the violet emission, in this case, this band is near to the range of the emission. When you measure, for example, photoluminescence from where, for example, this emission was obtained without 350 nanometers. Okay,
Yes.
and it's possible this band, there are relations in this mission. The violet bands, there are no explanation for this band. But for example, some works talk blue, green, violet blue. However, if this band is not adjusted, don't can just is spectrum. It's necessary for it. It was necessary for this band.
For making the convolution,
Yes,
you need this band.
yes.
But you say I cannot explain it.
Not really, because I probability there are defects. In this case, I don't know, or I don't search some time defects. And it's possible there are defects with the tail and tail bands. Band to band, no, tail. Tail to tail. Probably.
Yes.
Probably.
You need to see more detail.
Okay.
Okay.
Yes.
In order to have an explanation for that.
Yes.
So that even it is high intensity compared to the other.
Yes.
Okay. So second is
Thank you.
Any other questions, comments? So, thank you, Marcela. Oh, okay. Yes. Sure.
You said thickness decreases with temperature, right?
What?
Thickness of your samples
Okay, yes,
is decreasing, right? With
Yes.
increasing temperatures.
yes,
Can you explain this?
yes.
Yeah.
Okay. In this case, the acid positive presents 247 nanometers. However, when the temperature, many bonds are broken and and density are reduced. with the temperature. And when they increase the temperature, the bonds,
Which kind of bonds?
yes,
Can explain.
yes, okay. For example, we can observe with SEM, the as deposit and aluminum film, we can observe the remove the OH and CH bonds. The thickness reduce and compact.
Thank you.
Any other comments, question? No, okay. So thank you very much. So the session is over. Thank you for the participation. Gracias por.
Gracias.
Very lovely.